In this video, we're going to look at the concept of independence. We're going to understand the difference between dependent and independent events, know the effect of independence on the product rule, and be able to apply tree diagrams to a variety of different situations, and talk about the difference between mutually exclusive and independent. So first, let's define these terms. Two events A and B are called independent if the probability of A given B is equal to the probability of A. Another way of thinking about this is if knowing B does not affect A's probability, that the probability of the two do not affect each other. We can think about where this word comes from. Why do we use the word independent? You think if you are independent from your parents, then you are separate from them, and what they do doesn't affect you. However, if two events are dependent, then the probability of A given B is not equal to the probability of A. That means that knowing B does affect A's probability in some way. And again, if you are dependent on your parents, if you're a dependent person, then what they do does affect you in some way. So we'll understand these definitions with this example, and we'll talk about this for the rest of the video. So consider the following three basic events. P is the event that a person's name is Peter. J is the event that a person's last name is Johnson. And M is the event that a person is a male. So first question is, are the events P and M independent or dependent? So to look at this, we're going to look at the definition, and we're going to look at the conditional probability, the probability that M given P, and the probability of M, and see if they are equal or not equal. So let's think about these probabilities. First of all, the probability that a person is a male is about 50%. We're going to say it's about 50% of people are males, 50% are females. Then we have the question, what is the probability of someone as a male given that their name is Peter? Well, we're going to assume that most people, if not all people, whose name is Peter are males. So the probability that you're a male, given that your name is Peter, is very close to 100%. Even if there's some leeway involved, these two probabilities are definitely not the same, which means that these events are dependent. The idea that having a name being Peter affects the chance that somebody is a male. Now let's look at the events J and M, last name Johnson and person is a male. Again, the probability that somebody is a male is about 50%. And if we think about the probability that someone is a male given that their last name is Johnson, well, given somebody's last name doesn't tell us anything about the gender, so therefore this probability is still going to be 50%, which means that these things are equal, which means that these two events are independent. The fact that somebody's last name is Johnson gives us no information on whether they're a male or not, so they are independent events. So dependent means that they affect each other in some way, the probabilities do. Independent means that they are separate and they do not affect each other. So let's look at an example that we did in the previous video. Looking at the events, the first card is a heart, and the second card is a heart when we draw two cards from a deck of cards. Are these independent or dependent events? So we're going to call, in order to do this, we need to look at the probability that the first card is a heart and the probability that the second card is a heart, given that the first card is a heart. And if these two things are equal, then we know that these events are independent. And if they are not equal, then they are dependent. So we found that the probability that the first card is a heart is 13 out of 52. And we found the probability that the second card is a heart given the first card is a heart. We took the 13 over 52 and multiplied it by 12 over 51. Sorry, that's the probability of both being true. Here, we're just going to have the probability that the second card is a heart. We know there is one less card in the deck and one less heart. So there is 12 out of 51 chance that the second card is a heart. These two things are not equal, so therefore our events are dependent. And it's great to have this mathematical formula we can use, but let's just try to think if this even makes sense. Would the first card being pulled being a heart, would that affect the probability of the second card being a heart? And the answer is yes, because you're taking out one heart from the deck, so there's less to choose from. Right, that's directly affecting the next card. If, however, let's make a note of this, if the card were replaced, after you drew it, then these events would be independent. All right, so that kind of idea, let's talk about this next example. We're rolling a single die twice, a six-sided die. So use probabilities in the definition of independence and dependence to see if the events that the first roll is a 3 and the second roll is a 3 are independent or dependent. And we're going to find that these are independent, and we'll show the reason why, for the same reason of our note here, that if you replace the cards in the deck, then those would be independent. Here, you're kind of replacing the chance of getting a 3 when you roll the die again. It's an equal chance. But let's use the probability. The probability that the first roll is a 3 is 1/6. And the probability that the second roll is a 3, given that the first roll is a 3, is also 1/6 because the first roll doesn't change anything about the second roll. It doesn't give us any more information. It doesn't change the probabilities. So since these two are equal, then this is a set of independent events. So often this idea of independence and mutual exclusivity are mixed up. We got to make sure that this is not done. Although it's a common mistake, it's a bad mistake. These are fundamentally different ideas, although they both have this idea of having two events that are separate from each other, not affecting. But the difference is this, that independence is talking about the probabilities do not affect each other. Mutual exclusivity is saying that these events can't happen at the same time. Those are fundamentally different ideas. So the next few examples, let's talk about asking are two events independent, and we'll also ask are they mutually exclusive. So first example, let F be the event a person has freckles. And R is going to be the event a person has red hair. Determine if these two events are independent. Do they affect each other? The answer is no. These are not independent because a person has a higher chance of having either freckles or red hair, whichever one you want to do. Let's say of having freckles if they have red hair. We say the probability of freckles given red hair is greater than the probability of just freckles. So they're not equal. So these are not going to be independent events. Next question, are they mutually exclusive? Mutually exclusive means we're looking at the set F intersect R. Can these two things happen at the same time? And they definitely can. That's kind of the whole part of the first question. There are people that have both red hair and freckles, so these are not mutually exclusive. So let's do this again. Let T be the event that a person is tall, and R be the event that a person has red hair. Determine if T and R are independent events. And here they are going to be independent because the fact that somebody has red hair does not affect the fact that they might be tall. Or at least I am unaware of that relationship, but we're going to just say that these two things do not affect each other, the fact you're being tall based on the fact that you have red hair, or vice versa. Are these mutually exclusive? And the answer is no, right? Can somebody be tall and have red hair? And the answer is yes, they definitely can. So that means that these are not mutually exclusive. So here's a couple examples where the answers for these two things do not match up, and that is going to be the case often. I should say that these events are not equal to the empty set. There are people who are both tall and have red hair. So let's look at a couple bigger examples. First one is this newspaper poll about violence on TV we looked at in the previous video. 600 people are asked, what is your opinion on the amount of violence on TV? Is there too much violence? Yes, no, I don't know. And the results of the survey are broken down between men and women. So we looked at this, looking at conditional probabilities, looked at this example. Now let's talk about independence. Are the two events thinking there's too much violence on TV? That's going to be answering yes, that is Y. And being a man, M. Are they independent? So we are asking the question, is the probability of Y given M equal to the probability of Y? And note that we could also go the other way around. We could say, is the probability of M given Y equal to the probability of M? You could do it either way. So the probability of a yes answer, let's do that first. Let's look at just the yeses. Actually, we don't need to do that. The probability of yes is 418 over 600. When we think about yes given men, then we are looking at this men row as our total, looking at 280 as our new denominator. That's how many total men there are. And how many yeses are there out of that? 162. So the question here is, are these two fractions equal? And they are not equal. This is about 0.57. This is about 0.70. So since they are not equal, then they are dependent events. And you get the same result if you did the probability of men given Y and probability of men. We'll do that very quickly. Probability of men is going to be 280 over 600. And the probability of men given yes is going to be 418 is our new denominator and 162. And these are also not equal. So these are dependent events, which means that the fact that somebody is a man influences their choice of, or their response is the amount of, is there too much violence on TV? And lastly, we're going to look at the product rule for independent events. So this product rule we looked at for conditional probability, that said that the probability of A intersect B is equal to the probability of A given B times the probability of B. And now that we know that if A and B are independent, the probability of A given B is just equal to the probability of A, then we can replace this probability of A given B with probability of A and have this very nice formula that if A and B are independent, then the probability of the intersection is equal to the product of the probabilities. And note that's only true if A and B are independent. So if they are dependent events, you cannot use this nice formula, but we can if they are independent, and that's a very nice result going forward. So let's look at this. If a pair of dice is tossed twice, then find the probability that each toss is a 7. So that is the probability that the first toss is a 7 intersect the probability that the second toss is a 7. But we know that rolling a die twice, that's independent events. The second roll is not affected by the results of the first roll. Right? These are independent events. So therefore, we can write this as the probability that the first toss is a 7 times the probability that the second toss is a 7. So let's remember there are 36 total options for rolls of a pair of die. 6 options for the first and 6 options for the second. And the ways that we can get 7, we could have 1, 2, 3, 4, 5, or 6 on one die, and 6, 5, 4, 3, 2, 1 on the other die. So rolling a 1 and a 6, a 2, 5, a 3, 4, a 4, 3, a 5, 2, and a 6, 1 are all the ways we can get 7, and that is 6 options. So our probability is 6 over 36 for both. There is our probability. We can write that as 36 over 36 squared, which is 1 over 36.